At Artemis, we often talk about big visions, moon landings, gateway, the moon, or even Mars. But behind every vision, there's something much more mundane. Hardware, a lot of hardware, tons of hardware. And that's exactly what we're talking about today. Because Artemis 2 will be the first crewed mission with the Space Launch System, and therefore also the first real endurance test for a rocket that is technically impressive. Politically complicated and, let's say, financially controversial. Today, we're going to look at everything that makes this mission possible. The rocket itself, its stages, engines, upper stages, Orion, the launch escape tower, the ground facilities, the launch towers, and yes, also the people behind it. My name is Serwan, and this is Mars Chronicles. Let's start right at the top, or rather at the bottom, with the Space Launch System, or Space Launch System for short. The Space Launch System is currently the most powerful operational rocket in the world. Not the most modern, not the cheapest, but in terms of thrust alone, it's an absolute monster. If we take a sober look at the Artemis rocket, we're talking about a real heavyweight. The Space Launch System is about 98 meters tall and weighs around 2,600 tons at launch. It tips the scales at tons and generates a launch thrust of almost 4,000 tons. That means, in terms of thrust alone, the rocket even surpasses the legendary Saturn V, and that's already a pretty clear statement. Structurally, the Space Launch System basically consists of four major components. At the very bottom, or rather to the right and left of the orange core stage, are the two massive solid rocket boosters, which provide the lion's share of the power at launch. Each of these costs between 325 and 400 million United States dollars. In between is the large orange core stage, which carries the fuel and the main engines. This is based on the design of the external space shuttle tank. This core stage costs 1 billion United States dollars. That's 1,000 million. Completely over the top, if you ask me. And that doesn't even include the nearly 30 billion in development costs. On top of this core stage sit the upper stages, not because several are flying along, but because several upper stages were developed for the program. Or rather, for Artemis 2, they're still using the so-called interim cryogenic propulsion stage, which is basically a temporary solution. This stage flies on Artemis 1, 2 and 2I, and there's a massive problem that nobody talks about, but we'll get to that in a moment. This interim cryogenic propulsion stage is part of a contract worth 400 million, and a single stage alone costs between 40 and 50 million. Right at the very top of the system is Orion with the crew escape system. The development of the capsule has consumed about 20 billion United States dollars, and currently manufacturing a single capsule costs 1 billion. But Orion is useless without the European service module. And each of these ESMs also costs between 200 and 400 million euros. These four elements interlock like gears during launch, and that's why we're going to take a closer look at them step by step now. The two solid rocket boosters are the real powerhouses at launch. Each of these boosters consists of 5 segments. And yes, this hardware actually has a real Apollo and shuttle history. The boosters are directly based on the Space Shuttle's solid rocket boosters, but they are longer, more powerful, and have an additional segment. A single booster provides over 1,630 tons of thrust, and once ignited, burns relentlessly for about 2 minutes before being jettisoned and falling into the sea. But unlike with the shuttle, they are no longer recovered, but allowed to sink. The solid fuel consists of an aluminum-ammonium perchlorate mixture. Together, the two boosters provide the majority of the thrust during the launch phase. An interesting detail, many of the individual segments flying on the Space Launch System today have actually already been used on shuttle missions. The steel casings were recovered after each flight, inspected, refurbished, and reused. But I would be careful about using the word reuse here. The repeated use of these elements is more of a symbol than a cost-saving measure. However, Artemis 2 will also use new segments, since the shuttle program has been history for over 10 years. Production is now handled by Northrop Grumman in Utah. Then comes the centerpiece. The core stage, this huge orange central stage, is basically the rocket's tank and at the same time the engine module. It is about 65 meters long, has a diameter of 8.4 meters, and holds almost over 2 million liters of liquid oxygen and hydrogen. And at its lower end are 4 Rocketdyne 25 engines. These are perhaps the most fascinating relics in the history of space travel. Because these engines are not new developments, they are former space shuttle main engines. Extremely powerful, extremely efficient, but also extremely expensive. A single Rocketdyne 25 costs around 145 million euros to produce today. Back in the space shuttle days, they were reusable, but of course, that wouldn't even cross their minds today. The engines were converted from reusable to expendable mode for several billion United States dollars. You couldn't make this up. For Artemis 2, refurbished shuttle engines are still being used, and later Space Launch System flights will get newly built versions. Here are the performance specifications of an Rocketdyne 25. Each one delivers about 235 tons of thrust in vacuum, so that's almost 940 tons of thrust in total. The specific impulse is around 452 seconds, which is extremely efficient. The core stage burn time is about 8 minutes. This stage is basically a technical marvel, but it's also a prime example of why the Space Launch System is so expensive. And right at this point, we're going to take a short, very fitting detour. Because while the real Space Launch System rocket costs billions and is made up of thousands of special parts, we've built our own little version here in the studio. And we did it entirely with the Prusa Core 1. For this video, we printed a detailed model of the Artemis 2 configuration. Core stage, boosters, Orion, launch escape tower, the entire system, all made from individual parts, precise, stable, and surprisingly fast. And the great thing about it is that with a good 3D printer, spaceflight suddenly becomes tangible. You can not only look at the complex technology, but also touch it, take it apart, and understand it. The Core 1 is perfect for this. Enclosed housing, high print quality, reliable mechanics, and above all, extremely user-friendly. No matter if you want to print models of rockets, satellites, or entire space stations, this thing consistently delivers. But I also print a lot of my own stuff, like toys for my son, gifts to bring when visiting people, and household items. For example, here we printed the 5 segments of the boosters separately, the core stage in several parts, the launch escape tower in one piece, and even small details like adapters and stage connectors. So if you want to print models yourself, whether for space exploration, technical projects, or just for crafting, be sure to check out the Prusa Core 1. If you shop through my affiliate link, you get yourself something cool and help out directly. Mars Chronicles. Thanks to Prusa for the channel partnership. And now back to the real hardware, which unfortunately is a bit more expensive than the filament. And then this color. The famous orange isn't a design gimmick, it's simply the exposed insulation made of foam. If you want, you can do an experiment at home. Take a screenshot of the tank as it looks at the beginning of February and compare the photo with the Space Launch System in a few weeks. You'll notice that the tank has gotten a bit of color in the sun. The orange gets a little darker in the sunlight. Above the core stage sits the so-called Launch Vehicle Stage Adapter, an inconspicuous but important component. It connects the huge 8.4 meter core stage with the much smaller upper stage, and at the same time contains electronics and structural elements. Teledyne Brown Engineering manufactures this element and charges about 60 million for the first adapter, while the following ones will cost 85 million. However, this only applies as long as the interim cryogenic propulsion stage is flying. When the exploration upper stage or exploration upper stage flies, a new adapter will be needed, which will most likely be even more expensive. And this brings us to one of the most controversial points of the entire Space Launch System upper stage architecture. For Artemis 2, the so-called interim cryogenic propulsion stage, the interim cryogenic propulsion stage will still be used, and the word interim is the key to the problem here. Because from the very beginning, it was actually planned that the Space Launch System would fly with a more powerful upper stage, the exploration upper stage. And that's exactly where a piece of space policy begins that has been ignored by the public to this day. Originally, the plan was for the Space Launch System to fly with the exploration upper stage from the very beginning, which is being developed by Boeing. More power, more payload, better architecture. But the development of the exploration upper stage was delayed, and United Launch Alliance, a joint venture between Boeing and Lockheed Martin, made the following proposal. Let's build a transitional solution for these first flights. This transitional solution became the interim cryogenic propulsion stage. At its core, it's a slightly modified upper stage of the retired Delta IV rocket. The interim cryogenic propulsion stage has a single RL-10 engine and burns liquid hydrogen and oxygen. It delivers around 11.2 tons of thrust, so it's significantly less powerful than the planned exploration upper stage, and now comes the crucial point. This decision effectively created a two upper stage program. Instead of putting all resources into a single powerful upper stage, they developed the interim cryogenic propulsion stage as a transitional solution and, in parallel, the exploration upper stage as a long-term solution. That cost time and money, which was probably even intentional. Because they are still working with cost-plus contracts here, which means the slower and more expensive the project is, the more the contractors earn. But much worse than the costs and the wasted time is a problem that was created as a result, which still has an impact today. Because the result is the following. Artemis, I flew unmanned with the interim cryogenic propulsion stage. Artemis 2 will also fly manned with the interim cryogenic propulsion stage. That means there was an opportunity to at least test the upper stage under real conditions once without a crew before putting a crew on Artemis 2 and 2I. Artemis IV will be the first mission with the new exploration upper stage, and now it gets tricky. The first crewed mission with the exploration upper stage will also be its very first flight ever. No uncrewed test flight before, no real flight testing. From a safety perspective, let's say diplomatically, that's unusual. I would even go so far as to call this approach negligent. I brought this up with the then Chief Executive Officer of United Launch Alliance, Tory Bruno, on X, which was still called Twitter at the time, and he just blocked me. Actually, Artemis I could have been used perfectly to test the new upper stage without a crew. Instead, we're flying two crewed missions with a transitional stage, and then with Artemis IV, we're putting people directly onto a completely new upper stage. And that's exactly what we need to talk about. But before we get lost in this upper stage drama, there's still a crucial piece of hardware missing. The actual Orion spacecraft with the European Service Module, and the Launch Escape Tower, plus the launch towers and the entire ground system behind it. Because a rocket is just a transporter, and therefore only half the story, the real mission happens right on top of it. So let's talk now about what really makes Artemis II a lunar mission. Orion is National Aeronautics and Space Administration's crewed spacecraft, and unlike Apollo, Orion isn't a system for just a few days, but for real deep space missions. The capsule is about 3 meters tall and has a diameter of 5 meters. It has a launch mass of about 26 tons, and thanks to the European Service Module, can operate autonomously in space for up to 21 days. The European Service Module is built by the European Space Agency, more specifically by Airbus Defence and Space in Bremen. Some say that without Europe, Artemis simply wouldn't exist in this form, but National Aeronautics and Space Administration could certainly have come up with that extra billion and built the service module itself. It was more of a political favor, so that the closest ally would also have something to do. The European Service Module is a technical masterpiece, don't get me wrong, but the Americans could have done it themselves if they had wanted to. The European Service Module provides propulsion, power, oxygen, water, thermal control, and navigation. In short, everything that keeps the crew alive, and at the end of the mission, it is jettisoned and burns up. In the atmosphere, let's take a closer look at the European Service Module, because this is where Orion's real lifeline is found. The European Service Module is powered by 4 large solar panels and provides around 11 kilowatts of electrical power, enough to reliably operate all the systems on board. For propulsion, it uses a modified main engine that originally comes from the Space Shuttle program, specifically an adapted orbital maneuvering system engine. In addition, there are a total of 33 smaller thrusters responsible for attitude control and precise maneuvers. The service module uses the classic combination of monomethylhydrazine or monomethylhydrazine and nitrogen tetroxide as propellants. These are hypergolic fuels that ignite spontaneously upon contact, making them extremely reliable. All of this together makes the European service module the real workhorse of the mission, because without this module, Orion simply wouldn't be able to survive in space. That makes the cost structure even more interesting. Orion costs 1 billion and the European service module costs 250 million. And politically, the whole thing is clever as well. Europe builds the service module and in return gets seats for its own astronauts on Artemis missions. Jeremy Hansen on Artemis 2 is Canadian. On the next mission, a Japanese astronaut will fly, and only after that will a European astronaut go. Europe is clearly their junior partner, with little bargaining power and no real guarantee of participation. To this day, there is no assurance for European Space Agency as to when a European astronaut will actually be able to fly. The Orion capsule itself is basically a modern reinterpretation of the classic Apollo concept. It has room for 4 astronauts, is specifically designed for missions beyond Earth's orbit, and is significantly larger and more comfortable than the old Apollo capsules. Inside, it features state-of-the-art avionics, digital displays, new navigation systems, and advanced life support. So at first glance, it's a 21st century spacecraft. And yet, Orion's basic architecture follows a very familiar logic. Capsule design, massive heat shield, parachutes, and finally a splashdown in the Pacific, basically just like over 50 years ago. This combination is proven, robust, and safe, but it also brings back old challenges. The heat shield is one of the mission's most critical components. Because Orion doesn't return like a spacecraft from the International Space Station at around 28,000 km/h, but from a real lunar orbit at about 40,000 km/h, that's a massive difference. The thermal loads during re-entry are therefore significantly higher than with any normal return from Earth orbit. We're talking about temperatures of almost 2,800 degrees Celsius and extreme mechanical forces. And this is exactly where there was a serious warning signal with Artemis IV. During the unmanned test mission in 2022, the heat shield showed unexpected damage after returning. During the so-called skip re-entry, where Orion briefly skips over the atmosphere like a flat stone, heat pockets formed under some of the protective tiles. These caused pieces of material to be blown out in several places, resulting in significantly more wear than the engineers had expected. National Aeronautics and Space Administration analyzed this problem for 2 years afterward, evaluated data, and conducted tests. That's why the re-entry profile was adjusted for Artemis II. The skip re-entry will be flown in a modified form to avoid exactly this heat buildup. Instead of several skips through the atmosphere, Orion is now supposed to slow down more directly. That sounds like a small change, but it's a crucial difference for the safety of the crew. But I'm interested in what your gut feeling says about this. Please write it in the comments for me. Before we talk about the city towers and ground facilities, there's still an extremely important piece of hardware missing. The rescue tower, officially called the Launch Escape System or Launch Escape System, that's the pointed tower right on top of Orion. Its only job, if something goes wrong during launch, it pulls the capsule away from the rocket in a split second with an extremely powerful solid fuel engine. Thrust over 180 tons, activation time in milliseconds, a classic better safe than sorry system. Interesting detail. The tower is jettisoned after the most dangerous phase of the launch and burns up in the atmosphere, so it only flies along for the first few minutes. Now comes a point that is often completely forgotten or underestimated. A moon mission doesn't just consist of a rocket and a spacecraft, the entire ground infrastructure is at least just as important. And this is exactly where Artemis has one of its biggest and most expensive problems. Let's start with the Mobile Launch Tower, or Mobile Launch Tower for short. For Artemis 1 and 2, Mobile Launch Tower 1 is still being used. This is the modernized launch tower that was originally built for the Constellation program and then had to be modified for Space Launch System. Do you remember the thing with the interim cryogenic propulsion stage and exploration upper stage? This whole issue continues here. Now pay close attention. It is over 110 meters tall, weighs around 4,500 tons, and contains supply lines, elevators, access points, and fueling systems. Additionally, with the help of the crawler transporter, it can move the entire rocket from the vehicle assembly building, the nearly 7 kilometers, to pad 39B. That's really impressive. Mobile Launch Tower 1 has already successfully completed Artemis 1 and will also carry Artemis 2. So far, so good, but now comes the real drama. The Mobile Launch Tower 2, the second launch tower, is needed for the later Space Launch System versions with the large exploration upper stage. And this project is a textbook example of how space programs can get out of hand. If they had focused on the exploration upper stage from the start, they wouldn't have gotten themselves into this situation in the first place. The goal here was never to work efficiently, but let's stick with the Mobile Launch Tower 2. Originally, there was a pretty clear plan for the new Mobile Launch Tower 2, costs of around $380 million and completion in time for Artemis 4. That sounded manageable, predictable, and above all, realistic. However, reality now looks quite different. Today, the costs are already over $1 billion. The project is struggling with massive delays, technical problems, and an increasingly open dispute between National Aeronautics and Space Administration and the main contractor, Bechtel. There are internal reports stating that construction errors, poor planning, and constant design changes alone have consumed hundreds of millions of dollars. A perfect example of how a questionable decision can have cascading consequences. So we have the vehicle assembly building, the crawler transporters, the fueling systems, the communication networks, security systems, mission control in Houston, and launch control in Florida. All of that is also Artemis hardware, and that's still far from the end of the list. The Artemis hardware also includes National Aeronautics and Space Administration's globally distributed systems. The Deep Space Network, with its huge antennas in California, Spain, and Australia, maintains contact with Orion around the clock. In addition, there are communication satellites, tracking stations, and mobile ground antennas. Even recovery ships at sea, surveillance planes, weather reconnaissance, and emergency teams are part of this global network. So a moon mission is not just a rocket on a launch pad, but a planet-wide ecosystem that must work together perfectly from the first countdown to splashdown. And now comes a point that often gets completely overlooked in all the excitement about technology. People are also part of the hardware. With Artemis 2, the system is not just made up of metal and electronics, but of a huge network of experts. Of course, there's the actual crew who will eventually be sitting in Orion. But behind them are the astronauts' closest attendants, the suit technicians who prepare every detail of the spacesuits. Medical teams who constantly monitor the astronauts' health, flight directors who coordinate all decisions in the control center, and hundreds of engineers who work around the clock in mission control. In addition, there's the Red Crew, those who drive out to the fully fueled rocket at the last minute. As was the case with Artemis I, without this human hardware, literally not a single screw would work. Especially on a mission like Artemis 2, which is bringing people back into deep space for the first time in decades, this well-rehearsed orchestra of experience, training, and responsibility is at least as important as any turbopump or engine. If you look at it objectively, Artemis 2 is not actually as technologically revolutionary as it often sounds. The Space Launch System is essentially a mix of shuttle heritage and proven heavy rocket technology. Orion is a solid but rather conventional spacecraft built according to a classic design. The interim cryogenic propulsion stage upper stage is based on hardware that has been tested for decades, and the boosters are ultimately further developments of well-known systems. So the truly revolutionary aspect of Artemis 2 is not the technology itself, but something much more fundamental: the return of the ability to send humans beyond Earth orbit to the moon once again. It is precisely this capability, which was lost for decades after Apollo, that is being gradually rebuilt with this mission. And this is exactly where the irony lies. Artemis 2 is flying with a transitional solution, the interim cryogenic propulsion stage, to save a program that has been trying to be completed for over 10 years. Artemis 4 will then fly with the proper upper stage, but without having tested it unmanned beforehand. This is not an ideal path, but it's the path that was left politically. And with the new National Aeronautics and Space Administration Administrator, Jared Isaacman, the fate of the Space Launch System rocket is on shaky ground. That's why Artemis 2 is mainly the point where the whole house of cards has to show whether it can hold. If this mission works, then Artemis III becomes more realistic and the entire lunar architecture becomes more stable. If it fails, the whole program is in jeopardy. You can criticize Space Launch System and Artemis for many reasons: too expensive, too slow, too complex, and politically overloaded. But in the end, the fact remains: without this hardware, there is currently no realistic way back to the moon. SPACX is at least 2 years away from having this capability, and Blue Origin even longer. That's why Artemis 2 is less of a technical milestone and more of a political technological turning point, and that brings us full circle. Artemis 2, it's not a perfect system, it's a system full of compromises, but it's the system we have. And in February 2026, if everything goes well, this very system will have to prove that it works. My name is Serwan, and this was Mars Chronicles. Thank you for tuning in. Pera spera ad astra. Take two. But a planet-wide route